In this video, I will teach you about related rates. For example, when water is drained out of a conical tank, the volume V, the radius r, and the height h of the water level are all functions of time t. Find an equation relating the rate of change of the volume, the rate of change of the radius, and the rate of change of the height of the water level. And you can see the height of the water level here in the diagram with radius r and height h. But the quantity that ties all of these variables together is the volume. So you should probably memorize the following formula for the volume of a cone. The volume is equal to pi over 3 r squared h. When they ask us for an equation relating the rate of change of the volume, the rate of change of the radius, and the rate of change of the height of the water level, every time you see rate of change, you should be thinking d dt. So when they ask for the rate of change of the volume, that's dv dt. The rate of change of the radius would be dr dt. And the rate of change of the height of the water level would be dh dt. So the way we can get these quantities into an equation is to use implicit differentiation, and let's differentiate both sides of the equation so that these quantities will appear. All right, so as we differentiate both sides of the equation, so we will have d dt on the left, and we will have d dt on the right. So on the left-hand side, we already have one of the quantities we're looking for, dv dt. That's all done. Let's work on the right-hand side. First of all, we have a constant here in the front. When you take the derivative of a term, if there's a constant, you can bring that out front. So I'm just going to go ahead and put the pi over 3 out in the front, and then I'm going to go ahead and take the derivative of the rest. So now I'm doing d dt of my r squared h. This is a product, so let's go ahead and do the product rule here. So remember, the product rule tells us that we will basically do the derivative of the first one, and then later we'll do the derivative of the second one. Here's what I mean. We will do the derivative of r squared first, and right now we will leave the h part alone. Okay, now I'm going to put plus. For the second term, I'm going to end up taking the derivative of the second factor. So I'm going to leave the r squared alone, and I'm going to take the derivative of the h. All right, so how do I do this? So I think I'll go ahead and write the rest of my equation right now. So we still have this pi over 3 constant in the front, and we already have our nice dv dt all set up. So really just follow the ddt's because that's where all the action is happening. So it's time to take the derivative of the r squared. So the derivative of r squared is going to be 2r. We're using the power rule, and that 2 is going to come in the front, so we're going to end up with 2r. However, notice that the variables are not the same. I have the t and the r. When the variables don't match, you actually have to look at this as the chain rule. So when we move the 2 to the front, that was the outer function. But then we have to go ahead and take the derivative of the inner function second and multiply. So of course the inner function is just r, and that gives us dr dt. And don't forget this h that we have hanging out right there. So times h, which I'll just stick right there. And then we have the r squared. And this is just a single variable, so we can just simply write dh dt. Okay? Now, meanwhile, I have this pi over 3 sitting out front. So that's it. We have found ourselves an equation relating the rate of change of the volume, the rate of change of the radius, and the rate of change of the height of the water level. If y equals x squared plus 3, find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. Let's start with the master equation, y equals x squared plus 3. I'm just going to write it here, spread out a little bit to make room for my ddt's. All right, so let's use implicit differentiation and just take the derivative of both sides. So I'm going to have a ddt right here. And as I take the derivative of the right-hand side, I'm just going to wind up taking the derivative of each term because that's how you do that. All right, let's see what we have. On the left-hand side, we simply have dy dt. That's all you can do with that. To take the derivative of x squared, I'm definitely going to use the power rule and put that 2 in the front. So I'm going to get 2x. However, we have to use the chain rule because the variables don't match. We have a t and an x. So really we've done the outer function, and now we have to find the derivative of the inner function and multiply it by that. So in other words, we need to multiply by dx dt. And then the derivative of a constant is just 0, so that's just going to disappear. So this is what we have. So we are supposed to find dy dt when x is equal to 1. And let's see, let me just emphasize this. So when x is equal to 1, given that dx dt is equal to 2 when x is equal to 1. So basically, we're just going to substitute these values into this little equation. We are looking for dy dt, and we already have that lined up and ready. When x is equal to 1, so I'm just going to substitute 1 for that. But we also know that dx dt is equal to 2. So I'm just going to put a 2 right here in for dx dt. So of course that is going to equal 4. All right, it's just that easy. Example 3, a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So let me just point out a couple quick things. So when they say that the radius is increasing at a constant rate, when you see that word rate, that's rate of change. You should be thinking ddt. So they're talking about the radius r is increasing at a constant rate. So they're telling us that dr dt is a constant rate of 1. So they're telling us that dr dt equals 1. The second thing I wanted to point out is what we're looking for. What is the rate of change of the total area of the disturbed water? So we're trying to find dA dt. So keep those two things in mind. So as soon as they mention total area, well, that's something that we know a formula for. Simply the area of a circle is going to be pi r squared. So we can say A is equal to pi r squared. All right, I'm spacing this out a little bit to make room for my ddt's. I'm going to use implicit differentiation and take the derivative of both sides. So I'm going to put a ddt on the left-hand side. Now, I also need to put a ddt on the right-hand side. But because pi is a constant, let's put that in the front. So when you take the derivative, you can always put the constant in the front. So that's why I left this little space right here. So I can put my ddt right here. So that means on the left-hand side, we have dA dt, which is one of the things that we were looking for, the main thing we're looking for. And then on the right-hand side, we have pi times the derivative of r squared. So to do the derivative of r squared, we need to use the power rule and put that 2 in the front. So I'm going to have times 2r, but because the variables are different, this is going to be the chain rule. So there I've taken the derivative of the outer function, but now I need to multiply by the derivative of the inner function, which is simply dr dt. Okay, but remember, we are told that dr dt is equal to 1. So I can just go ahead and make that substitution right now. All right, so on the next step, I'm just going to have that dA dt is going to equal, okay, I'm going to go ahead and say pi times 2 times r. Well, we also know that because they said the radius is 4 feet. So I'm going to go ahead and put in 4 for r. And dr dt is 1. So I really don't need to write anything down. All right, it's just going to be 1. It's not going to affect anything. So I think it's time to go ahead and just say the final answer. So dA dt is going to equal 8 pi. Okay, and this is a rate of area. So this is going to be, we're looking for the units. So the area is square feet. So this is going to be square feet per second. So that's square feet per second. Let's do one more example. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So the first sentence, the air is being pumped in at a rate of 4.5 cubic feet per minute. When you see the word rate, you should be thinking dt. Now, the rate of what? Cubic feet per minute. That is volume. So we are being told that dV dt, all right, the rate of change of the volume is 4.5 cubic feet per minute. Now, we are supposed to find the rate of change of the radius. So we are looking for dr dt. Question mark. But we are given that the radius is 2 feet. So we're given two rates. No, we are given a rate and a radius, and we're looking for another rate. But as soon as you see this dV dt, volume, we know the formula for the volume of a sphere. So that's where you want to start, the formula that sort of relates the other variables. And we know that volume of a sphere is equal to 4/3 pi times the radius cubed. And again, the reason why I'm leaving this little space here is because I'm planning ahead. We are going to use implicit differentiation and differentiate both sides of this equation. So I'm going to put a d dt on the left, and normally I'd put a d dt right here in the front as I'm taking the derivative of the right-hand side of the equation. But these first characters here are constants, and we always put the constant out in front. So that's why I'm going to put my d dt right here, and I left a little space for it. Okay, so now what do I do? So I have dv dt. Remember that? We have a constant for that coming up soon. And that's going to equal 4/3 pi. Now, we need to take the derivative of r cubed. So we will do the power rule and put this 3 in the front. So that's going to be 3r squared as we reduce this by 1. But because these variables don't match, we have the t and the r, we now must use the chain rule and multiply by the derivative of r. So in other words, we have now done the outer function by moving the 3 out front and making it r squared, but now we have to multiply by the derivative of the inner function, which is simply going to be dr dt. All right, what can we substitute? We know that dv dt is 4.5, so I'm going to take that and I'm going to put it right here. So that will give us 4.5 is equal to 4/3 pi times 3, and we also know that r is equal to 2. So we can put 2 squared right here. And that'll be times dr dt. Dr dt is what we are looking for, so that is the only variable here. So it should be a simple matter of some arithmetic, really, to get dr dt by itself, a tiny bit of algebra. So let's simplify it out. So 4.5, by the way, is the same thing as 9/2. So I'm going to go ahead and put that as a fraction for now. And that equals 4/3 pi. Well, 2 squared is 4, and 4 times 3 is 12. So I'm going to have 12 dr dt. Awesome. 3 goes into 12 4 times, and 4 times 4 is 16. So I'm going to have 9/2 is equal to 16 pi dr dt. Okay, I always like to have this in yellow just to emphasize what I'm looking for. So, of course, now I am going to divide both sides by 16 pi. So that's going to wind up looking like this. I'm going to have my 9/2. When I divide by 16 pi, it's just going to end up in the denominator. All right, that's what happens when you divide a fraction by something. You just put that something in the denominator is all. And that equals dr dt, remember, which is what we are looking for. So I can simplify this a little bit by having 9/32 pi. So as far as an exact answer, this is the best we can do, dr dt. So that is the exact answer right here, kabam. You know what, I should put units on here. Maybe I'll put the units on my approximation. So dr dt is approximately 0.09, and we're talking about the rate of change of the radius, which is a length, and this was measured in feet. So we will say feet per, and time was measured in minutes. All right, so approximately 0.09 feet per minute.